In this video, we'll introduce L'Hopital's rule, which is a method you can use to compute limits. So let's recall for a moment what exactly we're doing here. We're computing the limit as x approaches a of some function f of x. And what is this? This is a number, and it's the number that the function f gets close to as x gets close to a. So let's think about some easy examples. Let's think about the limit as x approaches 3 of the function x squared plus 1. Now, the function x squared plus 1 is a nice quadratic. We could sketch its graph, for example, and it would be easy to show that the limit here is 10. Now, the function x squared plus 1 has this special property that it's a continuous function. And a continuous function, by definition, is one where if you want to compute a limit, all you do is plug the value 3, in this case, into the function, and we get 10 back. So this is a particularly easy limit to compute. Let's do something slightly more complicated. Let's compute the limit as x approaches 0 of a fraction. Let's take the fraction 7x squared minus x over x squared plus 4x. Now, if we just take the value 0 and plug it into this fraction, what happens? Well, we get 0 minus 0 divided by 0 plus 0. So we get 0 divided by 0, and that's clearly a bad thing. On the other hand, if we take any number that's not 0 and plug into this, then you'll just be able to cancel 1 power of that number everywhere. In essence, what we're saying is that this limit is equal to the limit as x approaches 0 of the same function where we've canceled out one of the x's. These two functions are the same except at the value x equals 0, where this one has a problem, but this one doesn't. So if we want to compute the limit as x approaches 0, we could just plug x equals 0 into this function, and we would get minus 1 divided by 4, so minus 1/4. L'Hopital's rule is something to help us compute some limits of things like this that are slightly more complicated. So here's an example of one that's slightly more complicated, and we can't just do this canceling procedure. The limit as x approaches 0 of the natural log of x plus 1 divided by x. So once again, this is a fraction. And if we plug x equals 0 into the top and the bottom separately, well, we get 0 on the bottom, and we get the natural log of 0 plus 1 on the top. And the natural log of 1 is also 0. So this is something which, if we just plug in the value, we get 0 over 0. That was the problem we had in the second example. But in the second example, we could do this cancellation trick. L'Hopital's rule, on the other hand, is precisely designed to compute the limit in this case, where we can't do something like just cancel out some powers of x. So what does L'Hopital's rule actually say? Well, it says that if we're trying to compute the limit as x approaches a of a fraction, f of x over g of x, where f of a and g of a are both 0. So if we plug in this value, we just get 0 divided by 0. Then this limit is equal to another limit, which is hopefully easier to compute. And this other limit that we compute is where you take the derivatives of f and g separately. So it's the limit as x approaches a of the derivative of f divided by the derivative of g. And at this point, hopefully we can just plug in x equals a in these two functions and just get a value out. If you can't, on the other hand, we can apply L'Hopital's rule again. And so this would also be the same as the limit as x approaches a of the second derivatives if f prime of a equals g prime of a equals 0, and so on and so forth. So if you take the derivatives and you still get 0 when you plug in the value a, you can take one more derivative of each function and continue on. So let's return to our example of the limit as x approaches 0 of the natural log of x plus 1 divided by x. So if we plug in x equals 0, we get the natural log of 1, which is 0, and then we also get 0 in the denominator. So we've satisfied this condition. This condition is often expressed by saying that we have a limit of the form 0 over 0. So what we do is we take the derivative of the top. So I take the derivative of the natural log of x plus 1, and that's 1 over x plus 1. Then I take the derivative of the bottom, which is just 1. And now I attempt to plug in x equals 0 again. And if I attempt to plug in x equals 0 again, I get 1 divided by 0 plus 1, all divided by 1. And you can see that that all simplifies to just the value 1. So L'Hopital's rule says if you have a limit of the form 0 over 0, then you take the original functions, replace the top one with its derivative, and the bottom one with its derivative, and then you try to take the limit again. Now, it's very important that what you don't do is take this function f of x divided by g of x and take the derivative of the whole function using the quotient rule. We're taking the derivatives separately. So the limit as x goes to a of f of x over g of x is equal to the limit as x goes to a of f prime of x over g prime of x if we're in the case where the limit is a 0 over 0 type. Now, one thing it is useful to note is that we can do this also when the limit is not to a specific number, but instead where x goes to infinity or perhaps minus infinity. And then we would just do the same thing. This is the limit as x goes to infinity or maybe minus infinity, once again, of the derivatives if we're in the case 0 over 0. Now, this is actually the easiest form of L'Hopital's rule. In the next video, we'll see that there are some other forms of L'Hopital's rule that apply to other circumstances besides 0 over 0, and perhaps require us to do some additional manipulations.